What keeps everything from floating away? Tonight we're going to explore gravity. You've felt it every single second of your life, keeping your feet on the ground, your coffee in your cup, the moon orbiting Earth. But here's what most people don't realize. Gravity isn't actually a force at all. It's something far stranger. A curvature in the very fabric of space and time itself. What we call gravity is really just objects following the straightest path through curved spacetime. By the end of this journey, you're going to understand why gravity is both the simplest and most mind-bending concept in physics. Before we dive in, if you enjoy these explorations, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a real difference for me. Dribble. Let's begin. You've felt it every single second of your life, keeping your feet on the ground, your coffee in your cup, the moon orbiting Earth. But here's what most people don't realize about gravity. It isn't actually a force at all. It's something far stranger, a curvature in the very fabric of space and time itself. What we call gravity is really just objects following the straightest path through curved space-time. By the end of this journey, you're going to understand why gravity is both the simplest and most mind-bending concept in physics. Let's start with something remarkable. Gravity is the most successful force in all of modern physics. Think about that for a moment. When you check your phone's GPS to navigate to an unfamiliar restaurant, you're relying on calculations that trace back to equations written over 3 centuries ago. Those satellites orbiting overhead, the ones that tell you exactly where you are on this planet, follow trajectories predicted with such extraordinary precision that they work perfectly, day after day, year after year. The equations Newton developed can calculate satellite orbits with accuracy so profound that our entire global navigation system depends on them functioning flawlessly. Every time you use GPS, you're witnessing the triumph of gravitational mathematics. Picture the complexity involved. Multiple satellites racing through space at thousands of miles per hour, their positions tracked to within meters as they orbit 12,000 miles above your head. The fact that your phone can pinpoint your location on a city street to within a few feet is nothing short of miraculous. Consider something as simple as dropping your keys. That mundane action represents one of the most precisely understood phenomena in all of science. The object falls with an acceleration of exactly 9.8 meters per second squared, regardless of where you are on Earth. Whether you're standing in Times Square or on a mountain peak in Tibet, whether it's your car keys or your wallet, the acceleration remains virtually constant. This isn't approximate physics. This is precision that would make a Swiss watchmaker envious. But here's what's truly extraordinary about this precision. Planetariums around the world project eclipses decades into the future using nothing more than formulas discovered in the 17th century. Astronomers can tell you exactly when the moon will pass in front of the sun on March 30th, 2033, down to the minute, and exactly which parts of Earth will witness totality. They've been doing this for generations, and they're never wrong. The gravitational constant itself, that fundamental number describing how masses attract each other, has been measured to extraordinary precision, 6.67 times 10 to the negative 11th meters cubed per kilogram per second squared. But here's where something fascinating and troubling begins to emerge. This mathematical precision creates a powerful illusion. Because we can predict gravity so perfectly, because the numbers work so elegantly, we assume we actually understand what gravity is. We mistake description for comprehension, confusing our ability to calculate with genuine insight into the phenomenon itself. Objects falling seem so natural, so obvious, that we rarely pause to ask the deeper question: why do masses attract each other at all? What is the actual physical mechanism that causes this attraction? When you drop that set of keys, what exactly makes them accelerate toward the ground? Children learn early that things fall down, and this apparent simplicity conceals one of the most profound gaps in our understanding of the physical world. The sensation of weight beneath your feet feels as fundamental as breathing, as if gravity were simply an intrinsic property of existence itself. You feel it when you wake up in the morning, when you climb stairs, when you sit in a chair. It's so constant, so reliable, that questioning its nature seems almost absurd. But that feeling of obviousness is deeply deceiving. Measurements reveal that Earth's gravity varies by only 0.5% between the equator and the poles, despite our planet's slightly flattened shape. This remarkable uniformity across our entire world makes gravity feel like a constant backdrop to reality, rather than a phenomenon that demands urgent explanation. Galileo Galilei demonstrated something in the late 1500s that challenged human intuition for millennia. When he conducted his famous experiments, dropping objects of different masses, he revealed that all objects fall at the same rate, regardless of their weight. A feather and a hammer, in the absence of air resistance, hit the ground simultaneously. This independence of mass was revolutionary, overturning thousands of years of accepted wisdom. For millennia, followers of Aristotle had believed that heavier objects naturally fell faster than lighter ones. It seemed logical, intuitive even. If you release a bowling ball and a tennis ball from the same height, shouldn't the heavier object fall faster? Our everyday experience, complicated by air resistance, seemed to confirm this ancient belief. But Galileo's careful experiments revealed that intuition, as we'll discover repeatedly throughout this journey, is a remarkably poor guide to understanding the universe. Newton's breakthrough came when he recognized that the same force pulling an apple toward Earth keeps the moon in its orbit around our planet. This insight represented the first great unification in physics, connecting terrestrial and celestial mechanics under a single mathematical framework. Before Newton, the heavens seemed to operate by entirely different rules than earthly phenomena. Planets moved in perfect circles, guided by celestial mechanics that appeared fundamentally distinct from the crude physics of falling rocks and rolling wheels on Earth. The gravitational force follows an elegant mathematical rule that governs interactions across the entire cosmos. It diminishes with the square of distance. Double the distance between two objects, and the gravitational attraction becomes 1/4 as strong. Triple the distance, and it becomes 1/9 as strong. This inverse square law works flawlessly across scales that boggle the human mind. From objects separated by centimeters in a laboratory to planets billions of kilometers apart in the outer solar system, the same mathematical relationship governs their gravitational interaction with unwavering consistency. Planets trace elliptical orbits around the Sun with such mathematical precision that we can predict their positions years, decades, even centuries into the future with margins of error measured in mere seconds of arc. To put that in perspective, a second of arc is roughly the width of a dime seen from 2 miles away. Halley's Comet provides one of the most spectacular demonstrations of gravitational predictability. This cosmic wanderer returns every 76 years, exactly as Newton's equations predict, following an elongated elliptical orbit that takes it from the outer reaches of the solar system to a close approach with the Sun. It's a celestial clockwork that has never missed its appointment with our night sky. The comet's next return in 2061 has already been calculated with such precision that astronomers know exactly when it will be visible from each location on Earth. Ocean tides rise and fall following the moon's gravitational pull with such regularity that fishermen and sailors have planned their lives around these patterns for millennia. The gravitational dance between Earth, Moon, and Sun creates tidal patterns so predictable that tide tables can be calculated years in advance. Coastal communities worldwide synchronize their activities with these ancient rhythms, trusting in gravitational mathematics that never fails them. Space agencies routinely use gravitational slingshot maneuvers to accelerate spacecraft, a technique that depends entirely on the mathematical precision of Newtonian calculations. These gravity assists are like cosmic billiard shots using planetary gravity to boost spacecraft speed and change direction. The Voyager 1 probe managed to escape our solar system after visiting Jupiter, Saturn, Uranus, and Neptune, using nothing but gravity to increase its velocity at each planetary encounter. This spacecraft, launched in 1977, followed a trajectory calculated with such precision that it arrived at each giant planet exactly when predicted, sometimes after journeys lasting years through the vast emptiness of space. Imagine the confidence required to launch a mission based on calculations predicting where Jupiter would be 4 years in the future, or where Saturn would be 7 years after launch. Yet every prediction proved accurate to the minute. Even astronauts floating aboard the International Space Station haven't escaped gravity's pull. They experience weightlessness, not because gravity has disappeared, but because they're in permanent free fall around Earth. The station orbits at an altitude of 400 kilometers, where gravity still maintains 88% of its surface strength. The station and everyone aboard are simply falling toward Earth continuously, but moving fast enough sideways that they keep missing the planet. It's a controlled fall that creates the sensation of weightlessness. All of these phenomena, from GPS satellites to space station orbits, from tidal predictions to planetary positions, work impeccably using mathematics developed in the 17th century. No corrections needed, no adjustments required. The equations Newton wrote by candlelight in his Cambridge study still guide spacecraft to Mars and predict the intricate dance of planets with unwavering accuracy. This apparent completeness led 19th century physicists to an extraordinary and ultimately premature conclusion. They believed physics was essentially finished. Lord Kelvin famously declared that there was nothing fundamentally new left to discover in physics, only more precise measurements needed to fill in the remaining decimal places. Gravity seemed like a perfectly understood force, mathematically tamed and reduced to simple equations taught in introductory physics courses worldwide. The mathematical framework appeared so complete, so successful in every application, that many scientists believed they had reached the end of fundamental discovery. The universe seemed to operate like a vast, predictable machine, its every motion governed by Newton's elegant equations. Each confirmed prediction, each successful satellite launch, each accurately forecasted eclipse reinforced the growing confidence that gravity held no more deep mysteries waiting to be uncovered. The mathematical success was so complete, so overwhelming in its scope and precision, that it seemed to prove humanity had finally penetrated to the very essence of this fundamental force. But this sense of intellectual security was about to crumble in ways no one could have imagined. Astronomical observations were beginning to reveal tiny deviations from classical equations, discrepancies so minute they were almost invisible, yet undeniably real. These weren't measurement errors or instrumental problems. They were genuine departures from Newton's perfect mathematics, cracks in what had seemed like an unshakable foundation. The triumph of Newton's mathematics had become a subtle but powerful cognitive trap, creating the dangerous illusion that describing a phenomenon mathematically is equivalent to understanding its fundamental nature. We had confused the map with the territory, mistaking our mathematical descriptions for true comprehension of the underlying reality. Gravity works so magnificently in practice, predicts so perfectly, calculates so precisely, that we forgot to ask the most basic question: what is gravity actually beyond the mathematical equations that describe its effects? The obviousness of falling objects, the reliability of tidal cycles, the precision of orbital mechanics had masked a truth that would take centuries to uncover and longer still to fully appreciate. Nobody understood the fundamental mechanism by which masses attract each other. We had perfect equations describing the effect, mathematical tools of extraordinary power and precision, but no genuine comprehension of the cause. The most familiar force in our daily experience, the one we feel with every step, the one that shapes galaxies and guides planets, remained as fundamentally mysterious as it was when the first human watched the first object fall to the ground. We had learned to predict gravity's behavior with extraordinary precision, but its essential nature remained completely hidden from us, waiting in the shadows to reveal secrets that would shatter our comfortable assumptions about the nature of reality itself. And that was just the beginning of the story. The first crack in Newton's perfect edifice appeared in the most unlikely place. Not in some exotic corner of the cosmos, not in the behavior of distant stars or mysterious nebulae, but right here in our own solar system. The planet Mercury, that small sun-baked world racing around our star every 88 Earth days, was about to become the unlikely herald of a revolution in physics. Mercury holds the distinction of being our solar system's innermost planet, orbiting the Sun at an average distance of just 58 million kilometers. Its elliptical orbit brings it as close as 47 million kilometers to our star at its nearest approach, a point astronomers call perihelion. In Mercury's scorching neighborhood, temperatures soar to over 400 degrees Celsius, hot enough to melt lead. By the mid-19th century, astronomers had developed instruments of remarkable precision. They could track Mercury's orbital motion with exquisite accuracy, measuring the planet's position against the backdrop of stars to within fractions of an arcsecond. What they discovered was something subtly strange, a tiny deviation that would eventually topple the entire classical understanding of gravity. As Mercury orbits the Sun, its perihelion slowly advances around the Sun's equator. Picture the planet's elliptical orbit as a slowly rotating ellipse, with the point of closest approach gradually shifting position over time. This phenomenon, called precession, was not entirely unexpected. The gravitational pulls of Venus, Earth, Jupiter, and the other planets create small perturbations in Mercury's orbit, tugging it this way and that as the planets dance through their own orbital cycles. 19th century astronomers calculated these planetary perturbations with meticulous care. According to Newton's equations, the combined gravitational influences of all the other planets should cause Mercury's perihelion to advance by approximately 5,700 arcseconds per century. These calculations represented some of the most sophisticated applications of Newtonian mechanics ever attempted, requiring astronomers to account for the complex gravitational interactions of multiple massive bodies moving through three-dimensional space. But when astronomers compared their theoretical predictions with actual observations, they found something troubling. Mercury's perihelion was indeed advancing, but not by 5,700 arcseconds per century. It was advancing by 5,143 arcseconds per century. The difference was only 43 arcseconds per century, a discrepancy so small it might seem insignificant to anyone but an astronomer. To put this in perspective, 43 arcseconds per century equals approximately 0.2 degrees per century. That's roughly the width of a human hair seen from 10 meters away, spread across an entire century of time. You could watch Mercury for your entire lifetime and never notice this tiny deviation with the naked eye. Yet this minuscule discrepancy was unquestionably real. The precision of 19th century astronomical instruments had reached the point where measurement errors of only 0.1 arcseconds per century were possible. The observed deviation was more than 400 times larger than the margin of error, making it impossible to dismiss as observational uncertainty or instrumental defect. The astronomical community faced an uncomfortable truth. Newton's perfect mathematics, which had predicted every other planetary motion with flawless accuracy, was failing to account for Mercury's behavior. Something was wrong, and nobody knew what. Urbain Le Verrier, the brilliant French astronomer who had previously used gravitational mathematics to predict the existence of Neptune, proposed an elegant solution. Perhaps there was another planet orbiting between Mercury and the Sun, a small world that astronomers had never detected. Le Verrier calculated that such a planet with a mass about 1/17 that of Mercury would create exactly the additional gravitational perturbation needed to explain the anomalous precession. He named this hypothetical world Vulcan, after the Roman god of fire, an appropriate name for a planet that would orbit closer to the Sun than any known world. For decades, professional and amateur astronomers scanned the skies in search of Vulcan, paying particular attention during solar eclipses, when the sun's glare wouldn't overwhelm the faint light from a small planet. In 1859, Edmond Lescarbot, a French country doctor and amateur astronomer, reported observing a small dark object transiting the sun's disk. Le Verrier investigated personally and declared the observation authentic, proclaiming that Vulcan had finally been found. The astronomical community celebrated what seemed to be another triumph of gravitational theory. But subsequent observations failed to confirm Lescarbot's sighting. During the total solar eclipse of 1860, Le Verrier mobilized the entire French astronomical community to search for the elusive intramercurial planet. Teams of observers positioned themselves along the eclipse path, cameras and telescopes at the ready. Some reported seeing small dark objects crossing the sun, but none of these sightings could be independently verified or reproduced by other observers. As years passed without a confirmed detection of Vulcan, alternative explanations began to emerge. Some scientists proposed subtle modifications to Newton's law of gravitation. Perhaps the gravitational force didn't follow an exact inverse square law, but rather was proportional to 1 over distance squared, plus some tiny additional term, epsilon. This epsilon would be a minuscule number, just large enough to correct Mercury's orbit without significantly affecting the other planets. Other theorists suggested the existence of an asteroid belt between Mercury and the Sun, a collection of small rocky bodies whose combined gravitational influence could account for the observed precession. Still others proposed that the Sun itself might not be perfectly spherical, arguing that a slightly flattened solar shape could contribute an additional 0.254 arcseconds to Mercury's precession. But even accounting for solar obliqueness, the effect explained only a tiny fraction of the discrepancy, leaving about 42 arcseconds per century, completely without physical explanation. Each proposed solution seemed to create more problems than it solved, requiring increasingly elaborate modifications to well-established physical principles. The astronomical community found itself divided between skepticism about the observations themselves and increasingly desperate attempts to preserve Newtonian theory through additional hypotheses. Some astronomers questioned whether the measurements were truly as accurate as claimed. Others proposed ever more complex scenarios involving multiple undiscovered objects or subtle modifications to gravitational physics. For half a century, physicists maintained faith that the Mercury problem would eventually be resolved through more precise observations or minor adjustments to established gravitational theory. The faith was understandable, given Newton's extraordinary track record of success. For over 200 years, Newtonian mechanics had explained every astronomical phenomenon with remarkable accuracy. No one seriously questioned the fundamental validity of Newton's gravitational theory because it had accumulated such a spectacular record of confirmed predictions and practical applications. The anomaly of Mercury was viewed as an irritating technical detail, not as evidence of a fundamental flaw in our understanding of gravity itself. Physicists attempted to preserve the Newtonian framework at all costs, adding what amounted to modern epicycles to save the theory. Just as ancient Ptolemaic astronomers had added circles upon circles to maintain their Earth-centered model of the cosmos, 19th-century scientists proposed planet upon planet, modification upon modification, to preserve Newton's gravitational mechanics. This stubborn attachment to established theory reflects a recurring pattern in the history of science. Paradigms resist change even when confronted with mounting contradictory evidence. Decades later, philosopher Thomas Kuhn would describe this phenomenon as normal science, where anomalies are treated as puzzles to be solved within the existing theoretical framework rather than as challenges to the framework itself. Scientific revolutions occur only when anomalies accumulate sufficiently and an alternative theory emerges that offers a more elegant and comprehensive explanation of the phenomena. But in the case of Mercury's precession, the solution would come from a direction completely unexpected, not from adjustments to existing theory, but from a radical reimagining of the very nature of space and time. Throughout these decades of confusion and failed explanations, the tiny discrepancy remained like a thorn in the side of classical physics. It served as an uncomfortable reminder that even the most successful theories might harbor fundamental limitations invisible to their creators and practitioners. The irony is profound when considered in retrospect. An anomaly so small that it amounted to barely 1/100th of a degree per century would eventually reveal the inadequacy of the entire Newtonian conceptual structure for describing gravity. This minuscule deviation would prove to be the first whisper of a revolution that would transform our understanding of space, time, matter, and the very fabric of reality itself. Mercury's stubborn refusal to follow Newton's equations precisely was not a minor computational error or an observational artifact. It was the universe speaking in a quiet voice, trying to tell us that reality operates in ways radically different from what classical physics had imagined for centuries. The cosmos was patiently waiting for someone brilliant enough to listen to what it was trying to say through this tiny but persistent deviation in a small planet's orbit. But the astronomical community, comfortable in the success of Newtonian mechanics, was not yet ready to hear that whispered message. It would take the insight of an unknown patent clerk in Switzerland to finally understand what Mercury had been trying to tell us all along. Mercury's stubborn refusal to follow Newton's equations precisely was not a minor computational error or an observational artifact. It was the universe speaking in a quiet voice, trying to tell us that reality operates in ways radically different from what classical physics had imagined for centuries. The cosmos was patiently waiting for someone brilliant enough to listen to what it was trying to say through this tiny but persistent deviation in a small planet's orbit. But the astronomical community, comfortable in the success of Newtonian mechanics, was not yet ready to hear that whispered message. It would take the insight of an unknown patent clerk in Switzerland to finally understand what Mercury had been trying to tell us all along. In 1905, Albert Einstein published a paper that would forever change our understanding of space, time, and motion. His special theory of relativity revolutionized physics by establishing a fundamental truth that had eluded scientists for centuries. The speed of light is constant. No matter how fast you're moving, no matter whether you're approaching or receding from a light source, light always travels at exactly 300,000 kilometers per second. This constancy of light speed led to extraordinary consequences that violated every intuition about the nature of time itself. Einstein showed that time passes differently for observers moving at different velocities relative to each other, a phenomenon called relativistic time dilation. Time is not the absolute universal constant that Newton had assumed. Instead, time is flexible, malleable, dependent on motion in ways that defy common sense. But Einstein quickly realized that his special theory of relativity had a serious problem. Newton's theory of gravity assumed that gravitational effects were transmitted instantaneously across space. If the sun suddenly vanished, Earth would immediately fly off in a straight line, according to classical mechanics. Yet Einstein's relativity insisted that nothing, not even gravitational influence, could travel faster than the speed of light. This contradiction troubled Einstein deeply. How could gravity operate instantaneously in a universe where the maximum speed limit was 300,000 kilometers per second? He dedicated the next decade of his life to developing a theory that would incorporate gravity into the relativistic framework, a quest that would require him to master entirely new mathematical tools and concepts. The crucial insight came to Einstein in 1907, what he would later call the happiest thought of my life. He realized that gravity and acceleration are fundamentally indistinguishable. Imagine yourself in a windowless elevator. If someone accelerates the elevator upward, you feel pressed against the floor with exactly the same sensation you experience when standing still in Earth's gravitational field. Now here's the remarkable part. There is no experiment you can perform inside that closed elevator to determine whether you're accelerating through space or sitting stationary in a gravitational field. The two situations are physically equivalent, impossible to distinguish without looking outside. This principle of equivalence led Einstein to an extraordinary prediction. If a beam of light crosses the elevator while it's accelerating upward, the light appears to follow a curved path from the perspective of someone inside the elevator. Since gravity and acceleration are equivalent, light must also bend when passing through a gravitational field. This was a radically new prediction, completely absent from Newtonian theory, where light would always travel in perfectly straight lines. From this insight, Einstein reached an even more profound conclusion. Gravity is not a force pulling objects toward each other. Instead, gravity is the curvature of spacetime itself, caused by the presence of mass and energy. This conceptual revolution transformed our understanding of the very stage upon which cosmic drama unfolds. To visualize this, imagine a large elastic sheet stretched horizontally, representing flat spacetime without any mass present. The sheet is perfectly smooth, its geometry perfectly Euclidean, just like the space we experience in our everyday lives. Now place a heavy bowling ball in the center of the sheet. The ball creates a depression, curving the previously flat surface around itself. If you roll a marble near the edge of this curved region, it doesn't travel in a straight line across the original flat surface. Instead, it follows the curvature created by the bowling ball, spiraling inward in what appears to be an orbit. The marble isn't being pulled by some mysterious force emanating from the bowling ball. It's simply following the most direct path possible through the curved geometry. This two-dimensional analogy helps us visualize what happens in the real four-dimensional space-time of our universe. Mass and energy curve the fabric of space-time around them, and objects moving through this curved geometry follow paths that appear to be influenced by gravitational force. But there is no force. There is only geometry. The mathematics required to describe this curved space-time pushed Einstein to the very limits of his mathematical knowledge. He had to learn tensor calculus, a complex mathematical framework for describing curved geometries in multiple dimensions. Einstein's field equations relate the curvature of spacetime, represented by something called the Ricci tensor, to the distribution of mass and energy, represented by the stress-energy tensor. These field equations consist of 10 coupled, nonlinear partial differential equations of extraordinary complexity. They can be solved exactly only in cases with special symmetries that simplify the mathematics dramatically. Most realistic situations require approximations or numerical computations that would have been impossible in Einstein's era. But Einstein was able to apply his new equations to Mercury's problematic orbit. Using an approximation valid for the relatively weak gravitational field of the Sun, he calculated the additional relativistic correction to Mercury's Newtonian orbital motion. The calculation predicted an extra advancement of Mercury's perihelion of exactly 43 arcseconds per century. The agreement with observation was perfect, not approximately correct, not close enough for government work, but precisely, exactly right. Einstein had explained the anomalous precession without adjusting any parameters, without adding hypothetical planets, without modifying the fundamental laws of physics. The theory simply applied to the conditions of the solar system produced the observed number naturally from its fundamental equations. Einstein later described feeling heart palpitations when he saw the calculation work, as if something inside him had burst with scientific emotion. Unlike the hypothetical planet Vulcan, which required adding an entirely new element to the solar system, general relativity explained the Mercury anomaly using only the more elegant and comprehensive principles already built into the theory. The definitive confirmation came during the total solar eclipse of May 29, 1919. Arthur Eddington, the British astronomer, led an expedition to measure the deflection of starlight passing near the Sun during totality. According to Einstein's theory, the Sun's gravitational field should bend the path of light from distant stars, making them appear slightly displaced from their normal positions when the Sun lies between Earth and the star. Newton's theory would also predict some deflection if light consisted of particles affected by gravity. But Einstein's prediction was exactly twice the Newtonian value. Eddington's careful measurements showed that starlight was deflected by 1.75 arcseconds, precisely matching Einstein's prediction and definitively ruling out the classical alternative. The result catapulted Einstein to worldwide fame overnight. Newspaper headlines proclaimed the discovery of a new theory of the universe, and the German physicist became an instant international celebrity. The success seemed to validate the most radical reimagining of physical reality since Newton himself. General relativity redefined gravity, not as a force, but as the geometry of space-time itself. Objects follow what mathematicians call geodesics, the straightest possible paths through curved space-time. A freely falling apple follows a geodesic, experiencing no force whatsoever. The weightlessness experienced by astronauts in orbit results not from the absence of gravity, but from geodesic motion through curved space-time. Consider the Earth itself orbiting the Sun. Our planet doesn't remain in orbit because the Sun pulls it gravitationally. Instead, Earth follows a straight line through the four-dimensional curved geometry created by the Sun's mass. From our three-dimensional perspective, this straight line through curved spacetime appears as an elliptical orbit, but Earth is actually traveling the most direct route possible through the warped geometry of space and time. This conceptual transformation is profound beyond words. Gravity ceases to be something that acts upon objects and becomes instead a property of the stage upon which all physics occurs. Space and time themselves become dynamic, responsive to the presence of matter and energy, participants in the cosmic dance rather than merely its passive backdrop. The success of general relativity in explaining both Mercury's precession and the deflection of starlight seemed to indicate that gravity was finally understood in terms of space-time geometry. After centuries of treating gravity as a mysterious force acting at a distance, Einstein had revealed it to be the curvature of the very fabric of reality itself. The mathematical elegance was stunning, the conceptual revolution breathtaking, the empirical confirmations compelling. It appeared that humanity had finally penetrated to the geometric heart of gravitational phenomena, reducing the most pervasive force in the universe to pure mathematics and geometry. Yet even as physicists celebrated this geometric triumph, other developments in early 20th century science were revealing that reality at the smallest scales operated according to principles that seemed fundamentally incompatible with Einstein's smooth, deterministic spacetime. Quantum mechanics was beginning to emerge, and it would pose challenges to our understanding of gravity that persists to this day. But this sense of geometric completeness would soon be challenged when quantum physics began to reveal that reality at subatomic scales operates under principles radically different from the smooth, continuous spacetime that Einstein had so elegantly described. Yet even as physicists celebrated this geometric triumph, other developments in early 20th century science were revealing that reality at the smallest scales operated according to principles that seemed fundamentally incompatible with Einstein's smooth, deterministic spacetime. Quantum mechanics was beginning to emerge, and it would pose challenges to our understanding of gravity that persists to this day. But this sense of geometric completeness would soon be challenged when quantum physics began to reveal that reality at subatomic scales operates under principles radically different from the smooth, continuous spacetime that Einstein had so elegantly described. While Einstein was developing his geometric theory of gravity, another revolution was quietly unfolding in parallel, one that would prove even more shocking to our understanding of reality. In the early 1900s, physicists studying the behavior of matter at atomic and subatomic scales began discovering phenomena that defied every classical intuition about how the world should work. It began with Max Planck's desperate attempt to solve a seemingly mundane problem in 1900. When physicists tried to calculate how much energy a hot object should radiate, their equations predicted nonsensical results, suggesting that any heated body should emit infinite amounts of energy. Planck resolved this ultraviolet catastrophe by proposing something radical. Energy doesn't come in continuous amounts but arrives in discrete packets, which he called quanta. This quantization of energy was just the beginning. In 1913, Niels Bohr created a model of the atom where electrons orbit the nucleus in specific, allowed orbits with precisely defined energies. Electrons could jump between these energy levels by absorbing or emitting light, but they could never exist between the allowed states. It was as if nature had built-in parking spaces for electrons, with no standing allowed in between. Then, in 1927, Werner Heisenberg formulated his uncertainty principle, establishing a fundamental limit to what we can know about particles. You cannot simultaneously measure both the position and velocity of a particle with perfect precision. This isn't a limitation of our instruments or measurement techniques. It's a fundamental property of reality itself. The more precisely you know where a particle is, the less precisely you can know how fast it's moving, and vice versa. Quantum mechanics describes particles not as tiny billiard balls following definite paths, but as wave functions that represent probabilities. These waves tell us where a particle might be found when we measure it, but they cannot tell us where the particle actually is before measurement. The distinction is crucial. An electron doesn't have a definite position and velocity before measurement. It exists in a superposition of multiple possible states simultaneously, a phenomenon with no analog in our everyday classical experience. Imagine an electron that can occupy two different energy levels in an atom. In the classical world, the electron would be in one level or the other, but quantum mechanics tells us the electron can be in both energy levels at the same time, at least until someone measures which level it actually occupies. The act of measurement collapses the wave function, forcing the electron to choose a definite state. This quantum weirdness proved incredibly successful at describing 3 of the 4 fundamental forces of nature. The electromagnetic force, which governs everything from chemical bonds to radio waves, is mediated by photons, particles of light that carry the interaction between electric charges. The theory describing this interaction, quantum electrodynamics, makes predictions accurate to better than 1 part in a billion, making it perhaps the most precisely tested theory in all of science. The strong nuclear force responsible for holding quarks together inside protons and neutrons operates through the exchange of particles called gluons. The theory of quantum chromodynamics describes this force with remarkable success, explaining why atomic nuclei hold together despite the electromagnetic repulsion between positively charged protons. The weak nuclear force responsible for certain types of radioactive decay is mediated by massive particles called W and Z bosons. These particles were predicted by theory decades before they were actually discovered in particle accelerators in 1983, providing dramatic confirmation of quantum field theory's predictive power. All of these forces operate through the exchange of virtual particles, ephemeral entities that appear and disappear so quickly they seem to violate energy conservation. But Heisenberg's uncertainty principle allows this apparent violation for extremely brief periods. These virtual particles are the messengers of force, the quantum mechanical explanation for how one particle can influence another across empty space. But there's a glaring exception to this quantum success story. Gravity, the force that seems most familiar and well understood from our everyday experience, stubbornly resists all attempts to be incorporated into the quantum framework that so successfully describes the other 3 forces. When physicists try to treat gravity as a quantum field theory, where hypothetical particles called gravitons would mediate gravitational interactions, the mathematics produces infinitely large results that make no physical sense. These mathematical infinities, called ultraviolet divergences, appear whenever you try to calculate the probabilities of gravitational processes at very high energies. In other quantum field theories, physicists have developed a technique called renormalization to handle similar infinities. They systematically cancel the infinities by adjusting parameters in the theory, maintaining finite, measurable predictions that can be compared with experiments. It's a mathematical sleight of hand that works brilliantly for electromagnetic, strong and weak forces. But for gravity, renormalization fails catastrophically. The infinities reappear at every level of precision, indicating that the theory is fundamentally inconsistent mathematically when applied at high energies. No amount of mathematical manipulation can tame these gravitational infinities. They persist like mathematical demons, refusing to be exorcised by any known technique. The problem arises from a fundamental incompatibility between the classical nature of general relativity and the inherently quantum nature of the other forces. Einstein's theory treats gravity as the curvature of spacetime, where geometric quantities like curvature have well-defined values at every point. But quantum mechanics works with superpositions and inherent probabilities, not definite values. Consider a quantum particle that can be in 2 different locations simultaneously. If this particle has mass, it should curve spacetime at both locations simultaneously, creating a quantum superposition of different geometries. But general relativity has no way to describe spacetime in superposition, because geometry is treated as a classical field with well-defined curvature at each point. When physicists try to sum over all possible quantum geometries using the mathematical technique called path integration, which works perfectly for other quantum field theories, the calculation explodes into uncontrollable infinities. Unlike successful quantum theories, gravity refuses to behave quantum mechanically. The smooth continuous spacetime of Einstein's theory seems fundamentally incompatible with the discrete, probabilistic nature of quantum reality. The scales where quantum gravity effects become important are completely inaccessible to current experimental investigation. The relevant energy scale, called the Planck energy, is about a billion gigaelectron volts, far beyond the reach of any conceivable particle accelerator. To probe these energies directly, we would need to build an accelerator the size of our solar system. The corresponding length scale, the Planck length, is approximately 10⁻35 meters, a distance so small that it defies human comprehension. If you could magnify an atom to the size of the observable universe, the Planck length would still be smaller than a human cell. At these minuscule scales, quantum fluctuations of spacetime itself should dominate all physics completely. In this realm, spacetime would cease to be the smooth, continuous fabric that Einstein described. Instead, it would become a seething quantum foam, with virtual geometries appearing and disappearing constantly according to quantum principles. The very concepts of distance and duration might lose their meaning in this churning quantum maelstrom. Physicists have proposed various approaches to quantum gravity, but each faces fundamental challenges. String theory suggests that fundamental particles are actually tiny, one-dimensional vibrating strings existing in 10 or 11 dimensions, most of which are compactified and invisible to us. Different vibrational modes of these strings correspond to different particles, including a hypothetical graviton that would mediate gravitational force. Loop quantum gravity takes a different approach, attempting to quantize spacetime directly. This theory proposes that geometry itself is discrete, composed of networks of quantum connections that form a granular fabric underlying reality. Space would consist of tiny, indivisible units of area and volume, making the universe fundamentally digital rather than analog at its deepest level. Both approaches face the critical problem that they make no testable predictions because their effects would only appear at energies or scales completely inaccessible to current observation. We cannot build experiments to test theories that operate at the Planck scale, leaving quantum gravity in the uncomfortable realm of pure theoretical speculation. This leaves physics in an unprecedented situation. We have two incredibly successful theories that describe different aspects of reality with extraordinary accuracy, but they are fundamentally incompatible with each other. General relativity governs gravity and the large-scale structure of spacetime, while quantum mechanics describes the other three forces and the behavior of matter and energy. The irony runs even deeper when you consider Einstein's role in both theories. The same physicist who gave us the geometric theory of gravity also contributed to the founding of quantum mechanics through his explanation of the photoelectric effect. Yet Einstein never fully accepted the probabilistic interpretation of quantum theory. His famous declaration that God does not play dice with the universe expressed his philosophical discomfort with quantum mechanics' inherently random nature. Einstein spent the last decades of his life searching for a unified field theory that would merge gravity with electromagnetism, but he largely ignored the quantum revolution that was transforming physics around him. His geometric theory of gravity remains incompatible with the quantum theory he helped create, but never embraced philosophically. This incompatibility suggests that something fundamental is missing from our understanding. Perhaps our conception of gravity is incomplete. Perhaps quantum mechanics itself requires modification, or perhaps both theories are approximations to some deeper, more fundamental description of reality that we have yet to discover. The universe seems to be telling us that our current understanding, however successful in its respective domains, is ultimately inadequate to describe the deepest level of physical reality. Until we can bridge this gap between the quantum and the gravitational, we remain in the uncomfortable position of having two separate descriptions of reality, neither of which can fully account for the other. This incompatibility suggests that something fundamental is missing from our understanding. Perhaps our conception of gravity is incomplete. Perhaps quantum mechanics itself requires modification, or perhaps both theories are approximations to some deeper, more fundamental description of reality that we have yet to discover. The universe seems to be telling us that our current understanding, however successful in its respective domains, is ultimately inadequate to describe the deepest level of physical reality. Until we can bridge this gap between the quantum and the gravitational, we remain in the uncomfortable position of having two separate descriptions of reality, neither of which can fully account for the other. Nowhere does this tension between quantum mechanics and general relativity become more dramatic than in the most extreme objects in the universe. Einstein's equations predict that when enough mass concentrates in a small enough region, space-time curves so severely that it forms something from which nothing, not even light, can escape. These are black holes, regions where gravity becomes so intense that it warps the very fabric of reality beyond recognition. The boundary that defines a black hole is called the event horizon, determined by what physicists call the Schwarzschild radius. This is the critical distance from a concentrated mass where the escape velocity equals the speed of light. Once anything crosses this invisible boundary, it can never return to the outside universe. The event horizon is a one-way membrane in space-time, allowing matter and energy to fall inward, but forbidding any escape. To put this in perspective, Earth would become a black hole if you could compress our entire planet into a sphere just 9 millimeters in radius. All of Earth's mass, every mountain and ocean, every building and living thing, squeezed into a volume smaller than a marble. The Sun would form a black hole if compressed to a radius of approximately 3 kilometers, creating a gravitational field so intense that nothing could survive within millions of kilometers of its surface. Real black holes form when massive stars, those with more than 20 times the mass of our Sun, exhaust their nuclear fuel and can no longer generate the outward pressure needed to balance their own gravitational pull. In a catastrophic event called a supernova, the star's core collapses violently in less than a second, creating a black hole in one of nature's most spectacular displays of concentrated energy. At the center of our own galaxy, the Milky Way, lurks a supermassive black hole called Sagittarius A, containing approximately 4 million solar masses, confined within a region smaller than Mercury's orbit around the Sun. Astronomers have tracked individual stars orbiting this invisible monster at speeds of thousands of kilometers per second, their motion providing undeniable evidence of an enormously concentrated mass that emits no light. In April 2019, the Event Horizon Telescope captured humanity's first image of a black hole's event horizon, revealing the supermassive black hole in the galaxy Messier 87. The image showed a ring of glowing matter surrounding a central shadow, the black hole's silhouette against the luminous material spiraling into its gravitational embrace. This photograph represented one of the greatest achievements in observational astronomy, making visible the invisible and confirming Einstein's predictions in the most extreme gravitational environment in the known universe. But here's where general relativity encounters its most profound crisis. According to Einstein's equations, inside the event horizon, at the very center of a black hole, lies something called a singularity. This is a point where the curvature of spacetime becomes infinite, where density becomes infinite, where the known laws of physics simply collapse and cease to function. A singularity represents the ultimate limit of general relativity, the point where the theory predicts its own failure. Einstein's equations essentially throw up their hands and admit they cannot describe what happens at the center of a black hole. The mathematics produces infinities that have no physical meaning, suggesting that our understanding of gravity breaks down completely under these extreme conditions. Roger Penrose and Stephen Hawking proved that these singularities are not mathematical artifacts resulting from unrealistic assumptions about perfect symmetry. Their singularity theorems demonstrate rigorously that, under very general conditions, general relativity inevitably predicts the formation of singularities. The theory contains within itself the seeds of its own destruction, forecasting conditions where it must cease to be valid. This is profoundly unsettling. A theory that works magnificently everywhere else in the universe admits that it cannot describe what happens at the most extreme gravitational conditions. It's as if Newton's laws suddenly stopped working whenever you tried to calculate the motion of very fast objects, which is essentially what happened when special relativity revealed the limits of classical mechanics. But the quantum world offers an even stranger perspective on black holes. In 1974, Stephen Hawking made a discovery that shocked the physics community. Black holes are not perfectly black. They emit a faint thermal radiation due to quantum effects occurring near the event horizon. This Hawking radiation arises from the quantum vacuum's inherent uncertainty. Even in supposedly empty space, pairs of virtual particles constantly appear and disappear, borrowing energy from the vacuum for incredibly brief moments before annihilating each other. Near a black hole's event horizon, something remarkable happens to these virtual particle pairs. Occasionally, one particle from a virtual pair falls across the event horizon, while its partner escapes to infinity. The escaping particle becomes real, carrying away a tiny amount of energy from the black hole. From the outside observer's perspective, the black hole appears to glow with thermal radiation, slowly evaporating as it loses mass energy to this quantum process. The temperature of this Hawking radiation is inversely proportional to the black hole's mass, making it incredibly faint for stellar mass black holes. A black hole with the mass of our Sun would have a temperature of only 60 nanokelvins, far colder than the cosmic microwave background radiation that permeates space. Such a black hole would actually absorb more energy from the cosmic background than it radiates, growing rather than shrinking. But given enough time, truly enormous amounts of time, even the most massive black holes will eventually evaporate completely. A solar mass black hole would take approximately 10·67 years to disappear entirely, a span of time so vast it makes the current age of the universe, 13.8 billion years, seem like an instant. This is far longer than the time it will take for all the stars in the universe to burn out and die. The evaporation process creates a profound puzzle known as the black hole information paradox. When matter falls into a black hole, it carries with it quantum information about its internal state. But Hawking radiation appears to be completely thermal, carrying no specific information about the matter that created the black hole. If a black hole evaporates completely into thermal radiation, what happens to the quantum information that fell in? Quantum mechanics demands that information must be preserved in any physical process. You should, in principle, be able to reconstruct the initial state of any system by carefully analyzing all the products of its evolution. But thermal radiation is random, carrying no information about the specific quantum states that produced it. This creates a fundamental contradiction between quantum mechanics and general relativity. Leonard Susskind and Gerard 't Hooft proposed a radical solution called the holographic principle. They suggested that all the information falling into a black hole is somehow encoded on its two-dimensional event horizon surface, rather than in its three-dimensional interior volume. This would mean that the three-dimensional space we experience might not be fundamental, but rather an emergent property of information stored on a lower dimensional boundary. This holographic idea emerged from string theory's most successful application, the AD-CFT correspondence, which establishes an exact mathematical equivalence between gravity in certain curved spacetimes and quantum field theories on their boundaries. In these special cases, a complete description of gravitational physics in the interior space can be translated into the language of quantum field theory on the boundary surface. However, there's a crucial limitation. The AD-CFT correspondence applies to universes with negative cosmological constants, which curve space in a way that makes it contract rather than expand. But we live in a universe with a positive cosmological constant, causing space to expand at an accelerating rate. Attempts to extend holographic principles to our actual universe face severe technical difficulties that remain unresolved. Singularities appear not only at the centers of black holes, but also in cosmology, at the very beginning of our universe. General relativity predicts that 13.8 billion years ago, all the matter and energy in the observable universe was concentrated at a single point of infinite density and temperature, the Big Bang singularity. In the first moments after the Big Bang, when the universe was smaller than a proton and hotter than the interior of stars, quantum gravity effects should have dominated all physics completely. Without a theory of quantum gravity, we cannot rigorously describe what happened during the first 10⁻43 seconds after the Big Bang, a period called the Planck epoch. Cosmic inflation theory proposes that the universe underwent an exponential expansion during its first instance, but the nature of the hypothetical inflaton field and the initial conditions that triggered inflation remain speculative. We have compelling observational evidence for inflation's effects on the cosmic microwave background, but we lack a fundamental understanding of the physics that drove this remarkable process. Recent observations of gravitational waves from merging black holes have provided stunning confirmations of general relativity in strong field regimes, validating Einstein's theory under conditions of extreme space-time curvature. When black holes spiral into each other and merge, they create ripples in space-time itself that propagate across the universe at light speed, carrying information about the collision encoded in the pattern of stretching and compressing space. Yet, the moment of collision, when two event horizons merge and become one, and especially what happens to the singularities inside them, remains completely inaccessible to both observation and theoretical understanding. The merger process occurs entirely behind event horizons, hidden from external observers by the very nature of black hole physics. These observations reveal a troubling pattern. Every time we push our theories to their limits, every time we encounter the most extreme conditions in the universe, we find that our understanding breaks down. General relativity and quantum mechanics, our two most successful theories, seem fundamentally incompatible precisely where we need them most, at the smallest scales, the highest energies, and the most intense gravitational fields. The universe appears to be constructed in such a way that its most extreme phenomena require a level of understanding that continues to elude us. Yet the moment of collision where event horizons fuse and within them where singularities exist remain inaccessible both observationally and theoretically in any complete sense. This brings us to perhaps the most uncomfortable truth in modern physics. We live in a universe governed by two fundamental theories that are spectacularly successful in their respective domains, yet utterly incompatible with each other. General relativity describes gravity and the large-scale structure of spacetime with remarkable precision, while quantum mechanics governs the behavior of matter and energy at the smallest scales. These two pillars of modern physics refuse to coexist peacefully. General relativity works magnificently on cosmic scales. It predicts the expansion of the universe, explains the formation of galaxies and galaxy clusters, describes the behavior of gravitational waves rippling across billions of light-years of space. When astronomers observe the cosmic microwave background radiation, the afterglow of the Big Bang still visible today, they find patterns that match general relativity's predictions with extraordinary accuracy. Meanwhile, quantum mechanics dominates the atomic and subatomic world with equal authority. It explains the structure of matter, the periodic table of elements, the behavior of semiconductors that make possible every computer, smartphone, and electronic device in our modern world. Without quantum mechanics, we would have no understanding of chemistry, no transistors, no lasers, no MRI machines, no solar panels. In practice, physics manages to function because these two realms rarely overlap in our everyday experience. Gravity is utterly irrelevant when studying individual atoms, and quantum effects are negligible when calculating planetary orbits. An electron orbiting an atomic nucleus experiences electromagnetic forces that are about 10^39 times stronger than the gravitational attraction between the electron and nucleus. On human scales and larger, quantum uncertainties become so small they're completely undetectable. But when phenomena require both theories simultaneously, our current understanding simply breaks down. We encounter a fundamental limit of contemporary scientific knowledge, a boundary beyond which our most successful theoretical frameworks become powerless to describe reality. The interior of black holes represents one such frontier where intense gravity meets the smallest possible scales. As matter falls toward a singularity, it gets compressed to densities where quantum effects should become important. Yet we have no theory capable of describing quantum mechanics in the extreme gravitational environment near a singularity. The initial moment of the Big Bang presents another crucial case where the entire universe was smaller than an atom, with gravity and quantum mechanics inextricably intertwined in governing all physical processes. In those first instants, before the universe had expanded enough for the two theories to separate into their distinct domains, understanding required a unified description we simply don't possess. The problem runs deeper than mere technical difficulties. The two theories operate with radically different philosophical assumptions about the fundamental nature of physical reality. They speak different mathematical languages and embody incompatible worldviews about how the universe works at its deepest level. General relativity assumes spacetime is smooth and continuous, with well-defined geometric properties at every point. Einstein's field equations are deterministic differential equations that, given initial conditions, predict the future evolution of space-time curvature with mathematical certainty. There's no room for probability or uncertainty in classical general relativity. Quantum mechanics, by contrast, works with discretization, superposition, and intrinsic probability. The state of a quantum system exists in superposition until measurement collapses the wave function into a definite outcome, but the specific result of any individual measurement remains fundamentally random. Quantum mechanics doesn't just use probability as a computational convenience. Probability is built into the very fabric of quantum reality. When physicists try to quantize geometry itself, they encounter superpositions of different spacetimes. A quantum particle that can be in multiple places simultaneously should curve spacetime in multiple ways simultaneously, creating a quantum superposition of different geometries. But general relativity provides no framework for adding together or comparing geometries in quantum superposition. It's like trying to mix oil and water. Each theory has its own mathematical language, conceptual structure, and domain of validity, with no obvious translation between these different paradigmatic frameworks. The mathematics of curved space-time geometry and the mathematics of quantum probability amplitudes seem to resist all attempts at unification. String theory represents the most ambitious attempt to bridge this gap. Instead of treating fundamental particles as mathematical points, string theory proposes they are tiny, one-dimensional, vibrating strings existing in 10 or 11 spatial dimensions. Different vibrational modes of these strings correspond to different particles, including a hypothetical graviton. that would mediate gravitational interactions, just as photons mediate electromagnetic interactions. The strings themselves extend over the Planck length, about 10⁻35 meters, which smooths out the ultraviolet divergences that plague attempts to treat gravity as an ordinary quantum field theory. By replacing point particles with extended strings, the theory avoids the mathematical infinities that make quantum gravity so problematic. But string theory requires 6 or 7 extra spatial dimensions beyond the 3 we observe directly. These extra dimensions must be compactified, rolled up in complex geometrical structures called Calabi-Yau manifolds that are invisible to us because they're curled up at every point in space at scales far too small to detect. The problem is that there are approximately 10,500 different ways to compactify these extra dimensions. Each different compactification produces different physics in our observable four-dimensional spacetime, creating what physicists call the landscape of possible vacuum states. This enormous number of possibilities prevents string theory from making unique, testable predictions about our particular universe. With so many possible solutions, almost any conceivable phenomenon can be accommodated somewhere in this vast landscape of theoretical possibilities. String theory becomes so flexible that it loses predictive power, making it difficult to test experimentally, or even to falsify through observation. Despite decades of intensive research, string theory has not yet been confirmed experimentally. The Large Hadron Collider, our most powerful particle accelerator, has found no evidence for supersymmetric particles predicted by string theory, even after extensive searches at energy scales where such particles should have been detectable. Loop quantum gravity takes a completely different approach. Instead of adding extra dimensions, it attempts to quantize space-time directly, proposing that space itself consists of discrete, indivisible units. In this theory, space is not continuous, but composed of fundamental grains with areas of approximately 1069 square centimeters and quantized volumes. This approach creates a granular, digital universe at the Planck scale. Space becomes like a vast three-dimensional mesh of interconnected quantum spin networks, with geometry emerging from the quantum states of these elementary spatial building blocks. Loop quantum gravity has achieved some notable successes. It can reproduce the entropy of black holes calculated by Hawking by counting the microstates of quantum geometry at the event horizon, providing a potential resolution to some aspects of the black hole information paradox. However, the theory faces its own challenges. It has not yet demonstrated convincingly how to recover classical general relativity in the low energy limit where quantum effects should become negligible. The connection between the quantum and classical descriptions of geometry remains technically obscure. Both string theory and loop quantum gravity solve some problems while creating others. Neither offers a complete experimentally testable theory that definitively unifies gravity with quantum mechanics. We remain tantalizingly close to a theory of quantum gravity, yet frustratingly far from achieving it. Experimental tests of quantum gravity face nearly insurmountable challenges. The relevant energy scale, the Planck energy, is about 10 to the power 19 giga-electron volts, approximately a quadrillion times beyond the reach of any conceivable particle accelerator. To probe these energies directly would require building an accelerator larger than our solar system. Alternatively, physicists search for subtle quantum gravitational effects in ultra-high precision experiments. They look for minute deviations from the predictions of either general relativity or quantum mechanics that might reveal the influence of quantum gravitational phenomena. But such effects are expected to be extraordinarily small. Some physicists have proposed that gravity might not be a fundamental force at all. Perhaps it's an emergent phenomenon arising from more fundamental, microscopic degrees of freedom that we haven't yet identified, similar to how thermodynamic properties like temperature and pressure emerge from the statistical behavior of countless molecules. Eric Verlinde developed the intriguing idea of entropic gravity. In this approach, gravitational attraction emerges from thermodynamic tendencies for physical systems to maximize their informational entropy, analogous to how osmotic pressure in fluids arises from statistical mechanics rather than fundamental forces. If gravity is indeed emergent rather than fundamental, it might not require quantization in the traditional sense. Just as temperature is an emergent property that doesn't need its own quantum theory because it represents the average kinetic energy of microscopic particles, gravity might be a macroscopic manifestation of more fundamental quantum phenomena. Regardless of which approach ultimately proves correct, all physicists working on these problems agree on one crucial point. Our current understanding of gravity is fundamentally incomplete, missing a crucial piece of the puzzle that describes the deepest level of physical reality. We find ourselves in the peculiar position of having two magnificently successful theories that together describe virtually everything we observe in the universe, yet they cannot describe each other. Ors. It's as if we have two different languages for describing reality, each perfectly adequate in its own domain, but with no dictionary for translation between them. This incompleteness suggests that our journey toward understanding gravity has only just begun. To truly appreciate the depth of our predicament, we need to venture into the most extreme scales imaginable, where our familiar notions of space, time, and causality themselves begin to break down. At the heart of this breakdown lies a fundamental scale in nature called the Planck length, approximately 1.6 times 10 to the 35 meters, where space-time itself loses classical meaning and the smooth geometry that Einstein described dissolves into quantum uncertainty. To grasp just how minuscule this scale is, consider that a hydrogen atom, the smallest and simplest atom in nature, has a diameter of about 1 angstrom, or 10 to 10 meters. The Planck length is roughly 25 orders of magnitude smaller than even this tiny atomic scale. The disparity is so vast that if you could somehow magnify a hydrogen atom until it reached the size of Earth itself, stretching its electron cloud across continents and oceans, the Planck length would still be smaller than the original unmagnified atom. This comparison reveals something profound about the architecture of reality. We live in a universe where the scales of physical phenomena span an almost incomprehensible range, from the cosmic horizons billions of light years across down to quantum realms so small that our very concepts of measurement and observation lose their meaning entirely. At the Planck scale, quantum fluctuations of energy become so intense that they create virtual particle pairs dense enough to curve space-time violently. The smooth, continuous geometry that general relativity describes gives way to what physicists call quantum foam, a seething, chaotic landscape where space and time themselves become granular and probabilistic. Imagine the surface of the ocean viewed from a great height, appearing smooth and continuous, but as you zoom in closer, revealing waves, then ripples, then ultimately the discrete motion of individual water molecules. Similarly, the apparently smooth space-time of our everyday experience might dissolve into discrete quantum fluctuations when examined at the Planck scale. In this quantum foam, concepts like distance and duration, which seem so fundamental to our understanding of reality, lose their precise classical meaning entirely. The very notion of measuring a length becomes problematic when the measurement process itself involves quantum uncertainties larger than the quantity being measured. It's as if you were trying to measure the width of a thread using a ruler made of fog. The corresponding energy scale, called the Planck energy, contains approximately 1.22 billion joules. To put this extraordinary concentration in perspective, That's roughly equivalent to the energy stored in a full tank of gasoline, but concentrated in a single subatomic particle, smaller than any currently known constituent of matter. The energy density becomes so extreme that Einstein's equation ʻOumuamua suggests the particle would contain enough mass energy to significantly curve the space-time around it. If two particles could somehow collide at Planck energies, they would create a microscopic black hole that would evaporate instantly through Hawking radiation in a time interval called Planck time. This collision would represent the ultimate high-energy physics experiment, but one that exists only in theoretical imagination, since no conceivable technology could accelerate particles to such energies. Planck time represents the shortest meaningful duration in physics, approximately 5.4 times 10^44 seconds. This is the time it would take light traveling at the universe's absolute speed limit to cross the Planck length. To appreciate how brief this interval is, consider that there are more Planck time units in a single second than there are seconds in the entire history of the universe since the Big Bang. Before this moment after the Big Bang, when our universe was smaller than the Planck length and younger than Planck time, both general relativity and quantum mechanics become necessary to describe reality, yet they remain fundamentally incompatible with each other. It's during this earliest epoch that the universe's fundamental properties were established, yet it remains completely inaccessible to our current theoretical understanding. The density at which these theories collide is called Planck density, approximately 5.1 times 10^96 kilograms per cubic meter. To appreciate this extreme concentration of matter, consider that atomic nuclei, already incredibly dense, have densities of about 10^17 kilograms per cubic meter. A teaspoon of nuclear matter would weigh roughly 5 billion tons, yet this represents only a tiny fraction of Planck density. Even neutron stars, the densest known objects in the universe apart from black holes, reach densities of only about 10 to 18 kilograms per cubic meter. These stellar remnants pack the mass of our Sun into a sphere just 20 kilometers across, creating gravitational fields so intense that a sugar cube of neutron star material would weigh as much as Mount Everest. Yet, neutron star density remains 79 orders of magnitude below Planck density, a gap so enormous it defies human comprehension. Inside black holes, as matter approaches the central singularity, density theoretically increases without limit, eventually reaching and surpassing Planck density. At this point, our current physics simply fails completely. We have no idea whether space-time continues to exist in any meaningful sense, whether singularities are real physical objects, or whether they represent artifacts of classical theory applied inappropriately to quantum regimes where it no longer applies. The mathematical singularities predicted by general relativity might be signs that the theory has reached its limits, similar to how classical mechanics breaks down when applied to atomic scale phenomena. Just as Newtonian physics required replacement by quantum mechanics at small scales, general relativity might require replacement by quantum gravity at extremely high densities and curvatures. The frustrating reality is that astronomical observations provide little help in understanding these extreme conditions. Events occurring at Planck scales either happened billions of years ago during the first moments after the Big Bang, or they remain hidden behind event horizons, where they're fundamentally inaccessible to external observation. We cannot see into the heart of a black hole, nor can we directly observe the quantum gravitational processes that shape the universe's first instance. This observational barrier represents one of the deepest challenges in modern physics. Unlike other areas of science where theory and experiment can work hand in hand to test ideas against reality, quantum gravity exists in a realm where direct experimental verification seems impossible with any foreseeable technology. Our most powerful particle accelerator, the Large Hadron Collider, reaches energies of approximately 13 tera-electron volts. While this represents an impressive achievement in experimental physics, the result of international collaboration involving thousands of scientists and engineers, it falls short of Planck energies by a factor of about 10 $. The gap between achievable and relevant energies is so vast that it spans 15 orders of magnitude. To reach Planck, energies would require building an accelerator the size of an entire galaxy, a project that's completely impractical with any conceivable technology now or in the foreseeable future. The engineering challenges would be insurmountable, requiring materials and energy sources that exist only in science fiction. Even if such a machine were theoretically possible, the energies involved would be so extreme that they might create dangerous gravitational effects or microscopic black holes. This enormous gap between accessible and relevant energy scales forces physicists to search for subtle indirect effects of quantum gravity. They look for minute deviations in the propagation of light from distant sources, hoping to detect evidence that spacetime has a granular structure at the smallest scales. If space is indeed discrete rather than continuous, photons traveling across cosmic distances might accumulate tiny phase shifts that could eventually become detectable. Others search for violations of quantum entanglement correlations that might reveal the underlying quantum geometry of space itself. If space-time is fundamentally quantum mechanical, then the entanglement properties of quantum fields might be modified in ways that could be measured in ultra-precise experiments using advanced quantum technologies. Experiments test Einstein's equivalence principle with ever-increasing precision, seeking tiny violations that would indicate a quantum substructure to spacetime at scales far below current detection limits. The equivalence principle, which states that gravitational and inertial mass are exactly equal, represents one of the cornerstones of general relativity. Any deviation from perfect equivalence could provide evidence for the discrete, quantum nature of geometry at fundamental scales. Modern tests of equivalence can detect differences between gravitational and inertial mass at the level of parts in 10^13, and future experiments aim to push this precision even further. These tests use sophisticated techniques involving rotating masses, lunar laser ranging, and satellite-based experiments to search for the slightest hint that gravity behaves differently than Einstein predicted. Gravitational wave observations might eventually reveal frequency-dependent dispersion if spacetime is indeed granular rather than smooth. If space has a discrete structure at the Planck scale, gravitational waves of different frequencies might travel at slightly different speeds, similar to how different colors of light travel at different speeds through glass. Such dispersion effects would be extraordinarily small and difficult to detect reliably with current technology, but future gravitational wave detectors might achieve the necessary precision. The recent detection of gravitational waves from merging black holes and neutron stars has opened an entirely new window for testing fundamental physics. These observations allow us to study gravity in the strong field regime where deviations from general relativity might become apparent, complementing traditional astronomical observations with direct measurements of spacetime curvature itself. The cosmic microwave background radiation provides our most detailed information about the early universe, carrying signals from when the cosmos was only 380,000 years old. But this ancient light tells us nothing about the crucial first moments when quantum gravitational effects dominated all physics. The universe was opaque to electromagnetic radiation during its first 380,000 years, hiding the details of its quantum gravitational birth from direct observation. However, if primordial gravitational waves from cosmic inflation could be detected, they would carry information about the universe's state during its first instance. These hypothetical waves would have been generated when the universe was smaller than a proton, and quantum effects were paramount, providing a direct probe of quantum gravity in action. The detection of such primordial gravitational waves would represent one of the greatest discoveries in cosmology, offering a window into the quantum gravitational processes that shaped our cosmos. Extreme scales also manifest in the accelerations experienced by matter near black hole event horizons. Small black holes undergoing evaporation can have surface accelerations reaching values that approach the realm where quantum fluctuations should completely dominate gravitational behavior. The event horizon of a solar mass black hole has a surface acceleration of approximately 1.5 times 10 to the 112 meters per second squared, already an almost incomprehensible value that would tear apart any material object. A hypothetical black hole with Planck mass, roughly 22 micrograms, would have surface accelerations approaching the scale where quantum effects and classical gravity become equally important. At these extreme accelerations, the very concept of a smooth event horizon breaks down, and quantum fluctuations of space-time itself become the dominant physical processes. Such tiny black holes would evaporate in times much shorter than Planck time, existing only as fleeting quantum fluctuations. Ingenious physicists have attempted to study black hole physics indirectly through analog systems created in laboratory settings. They use supersonic fluid flows or Bose-Einstein condensates to create analogs of event horizons, where sound waves or other excitations cannot escape past certain boundaries, mimicking some aspects of black hole behavior in controllable experimental environments. While these analog systems don't involve real gravity, they can test general principles of field theory in curved spacetimes. Researchers have observed analog versions of Hawking radiation in these systems, providing experimental confirmation that the theoretical framework underlying Hawking's predictions is at least partially correct, even if we cannot observe actual black hole evaporation directly. The fundamental question that haunts modern physics is whether space-time is truly granular at the Planck scale, or whether the smooth description of general relativity remains valid to arbitrarily small distances. This question goes to the heart of our understanding of reality itself. If space-time is indeed discrete at its foundation, then familiar concepts like locality, causality, and even time itself might be emergent approximations rather than fundamental features of the universe. In a granular space-time, the continuous flow of time we experience might be analogous to the smooth flow of water, which appears continuous to our senses, but actually consists of discrete molecules. At the deepest level, reality might operate more like a digital computer than the analog continuous processes described by classical physics. This digital universe would process information in discrete steps, with space and time emerging as computational concepts rather than fundamental geometric structures. If this granular picture is correct, then our most basic assumptions about the nature of space and time may be fundamentally misguided. The smooth space-time of Einstein's general relativity would be revealed as an emergent, approximate description that works well at large scales, but breaks down completely when we probe the ultimate foundations of geometric reality. Different approaches to quantum gravity make different predictions about the nature of space-time at the Planck scale. String theory suggests that space has extra dimensions compactified at every point, while loop quantum gravity proposes a discrete network of quantum geometric relationships. Each theory implies different signatures that might eventually be detectable through ultra-precise experiments or astronomical observations, though such tests remain at the very limits of technological possibility. Yet, despite decades of theoretical progress, we remain tantalizingly far from experimental verification of any quantum gravity theory. The energy scales involved are so extreme, and the expected effects so subtle, that definitive tests remain beyond our current technological capabilities. We find ourselves in the unusual position of having theories that make precise mathematical predictions about phenomena we cannot observe. Physics finds itself suspended between two abysses. On one side lie the immense scales of the cosmos, where dark matter and dark energy comprise 95% of the universe, yet remain completely mysterious in their fundamental nature. Galaxies rotate faster than they should, the universe expands at an accelerating rate, and we have no deep understanding of the forces driving these cosmic scale phenomena. On the other side lie the microscopic scales of quantum geometry, where space and time themselves might dissolve into something utterly alien to our everyday experience. Here, the familiar concepts of before and after, here and there, might lose their meaning entirely, replaced by quantum relationships that have no analog in our macroscopic world. Both extremes reveal that gravity continues to harbor profound mysteries that resist our attempts at understanding. Whether we look outward to the largest scales or inward to the smallest, we encounter phenomena that challenge the very foundations of our physical theories and force us to confront the limits of human comprehension. The universe seems designed to keep its deepest secrets just beyond our reach, always retreating into realms too large, too small, too energetic, or too subtle for our current understanding to grasp. Yet physics finds itself suspended between two abysses, the immense scales of the cosmos and the minute scales of quantum geometry, both revealing that gravity harbors profound, unsolved mysteries. Here lies a profound irony that should humble anyone who contemplates the trajectory of human knowledge. For 400 years since Newton, gravitational physics has progressed enormously in its mathematical sophistication and predictive power, yet paradoxically, our fundamental understanding has actually retreated, revealing layers of ignorance we didn't even know existed about the essential nature of reality itself. Newton himself was refreshingly honest about the limits of his understanding. He admitted openly that he didn't know what caused gravity, only how to describe its effects mathematically. His famous phrase, hypotheses non fingo siumos, I forge no hypotheses, reflected a deliberate restraint about the ultimate nature of gravitational phenomena. Newton gave us the mathematical tools to predict gravity's behavior with extraordinary precision, but he made no claims about understanding its fundamental essence. Einstein appeared to advance beyond Newton's limitations by revealing that gravity is geometry, showing us that massive objects curve the fabric of space-time itself. But this geometric insight, however profound and mathematically elegant, merely transferred the mystery to a deeper level. We still don't understand why mass curves space-time, or what space-time fundamentally is, beyond the mathematical formalism that describes its behavior. This pattern repeats throughout the history of physics. Each answer generates deeper questions, and scientific progress doesn't eliminate mystery, but rather displaces it to more fundamental layers of reality's causal structure. We solve problems only to discover that our solutions reveal new puzzles we couldn't even formulate before achieving our current level of understanding. Consider the practical situation we find ourselves in today. Gravity works perfectly for every technological application we can imagine. We launch satellites with precision, predict eclipses decades in advance, navigate spacecraft across billions of kilometers of space, yet we genuinely don't know what gravity is in any deep ontological sense. Our equations describe its behavior flawlessly, but they don't explain its nature. This profound disjunction between practical efficacy and conceptual understanding challenges our basic assumptions about what science accomplishes. Does science actually explain reality? Or does it merely provide increasingly sophisticated mathematical descriptions without capturing the true essence of natural phenomena? Philosophical instrumentalism argues that scientific theories should be understood as tools for making predictions rather than literal descriptions of reality. From this perspective, theories are useful models that help us organize observations and make accurate forecasts, but they carry no necessary commitment to the actual existence of the entities and processes they describe. Scientific realism counters by arguing that the predictive success of our theories would be an inexplicable miracle if they didn't capture something genuinely true about the deep structure of the universe. The extraordinary accuracy of gravitational predictions suggests that our mathematical descriptions must correspond to real features of physical reality, even if we don't fully comprehend what those features ultimately are. Gravity exposes the tension between these philosophical positions in the starkest possible terms. Our gravitational theories function marvelously for every practical purpose, yet they reveal themselves to be fundamentally incomprehensible when subjected to rigorous philosophical scrutiny that probes beyond their mathematical success. From an anthropocentric perspective, we might reasonably ask why we would expect the universe to be comprehensible to primates who evolved in African savannas only 200,000 years ago. The human brain evolved to help our ancestors survive in environments characterized by scales of meters and seconds, not to comprehend quantum singularities or space-time curvatures operating at Planck scales. Mathematics allows us to extend our intuitions far beyond the domain where they evolved, enabling us to describe phenomena that no human has ever directly experienced. But perhaps there are fundamental cognitive limits to what finite minds can genuinely comprehend, regardless of how sophisticated our mathematical tools become. Philosopher Colin McGinn proposed that just as rats cannot understand differential calculus, humans might be cognitively closed to certain fundamental aspects of physical reality. Our mental architecture might simply lack the conceptual resources necessary to grasp the true nature of phenomena like quantum gravity. Gravity might exemplify a phenomenon so fundamental that our evolved conceptual categories simply don't apply to its genuine nature. Perhaps gravity isn't too complex for human understanding, but rather too simple, too fundamental to be explained using concepts derived from our limited terrestrial experience. Attempting to explain gravity using supposedly more basic concepts might represent a categorical mistake, like trying to explain existence itself using concepts that already presuppose existence. Wittgenstein argued that explanations must terminate somewhere. We eventually reach bedrock foundations that simply are, without requiring deeper justification. Gravity might be one of these basic ontological foundations of reality, an aspect so primordial that it cannot be reduced to anything more fundamental. Alternatively, gravity might be an emergent phenomenon arising from some unknown microscopic structure, similar to how temperature emerges from molecular motion without being fundamental in itself. The existential irony is striking. The force that literally keeps us anchored to the ground, that we feel with every step and every breath, remains profoundly mysterious and incomprehensible in its ultimate essence. Gravity is the most immediate and constant experience of our lives, the weight of our bodies, objects falling when dropped, rain descending from clouds. This ubiquitous familiarity creates a powerful illusion of understanding. We assume we comprehend gravity because we experience it constantly, but subjective experience doesn't equate to objective physical understanding. A child quickly learns that things fall downward, but understanding why things fall required centuries of scientific development, revealing the vast distance between perceptual experience and theoretical knowledge. Even after Einstein, quantum mechanics, and decades of intensive theoretical work by brilliant minds, gravity continues to guard its essential secrets. This epistemic humility is crucial for the healthy progress of science. Knowledge advances by acknowledging ignorance rather than prematurely claiming understanding about phenomena that remain genuinely mysterious. The quest for quantum gravity represents more than just a technical problem to be solved. It constitutes a confrontation with the limits of human knowledge itself, raising fundamental questions about what finite minds can ultimately comprehend about the nature of reality. The answers we seek might not emerge in our generation, perhaps requiring conceptual leaps as radical as Einstein's relativity was compared to Newton's mechanics. Or perhaps we will never achieve complete understanding of gravity. Perhaps this fundamental force will remain permanently beyond the reach of human comprehension, serving as an eternal reminder that reality transcends our finite cognitive capacities. The failure to fully understand gravity would not represent a defect in the scientific enterprise, but rather a deep characteristic of the human condition. We are finite beings exploring a universe that was not constructed for our convenience or comprehension. The remarkable fact is not that we sometimes fail to understand natural phenomena, but that we understand as much as we do. Yet the mystery of gravity also reveals something inspiring about human nature. Despite our limitations, we continue to probe deeper, to ask more fundamental questions, to push against the boundaries of the knowable. We are beings who cannot help but wonder, who find deep satisfaction in the very process of questioning. In the end, our failure to fully comprehend gravity may not be a scientific problem to be solved, but rather a permanent feature of our relationship with reality. It reminds us that we are explorers in a universe that transcends our understanding, and perhaps that mystery itself is an essential part of what makes existence wonderful rather than merely mechanical. Our failure to comprehend gravity is not a scientific defect, but a profound characteristic of the human condition, exploring a universe that was never built to be fully comprehensible to us. Yet perhaps there's something deeply beautiful about learning to live with this mystery. The history of science reveals a recurring pattern that should teach us humility. Each major advance exposes new mysteries that are more profound than the problems it solved. Scientific progress doesn't eliminate ignorance, but transforms it, making it more sophisticated and often more troubling than before. Before Newton, gravity was a complete mystery. After Newton, it became a mathematically described mystery, predictable in its effects, but still fundamentally unexplained in its cause. After Einstein, gravity transformed into a geometrized mystery, elegant in its mathematical structure, yet still hiding its deepest nature behind the formalism of curved spacetime. This pattern extends far beyond gravity. Quantum mechanics resolved the crisis of atomic stability, but created interpretational paradoxes about the nature of reality that have persisted for over a century. Cosmology explained the expansion of the universe, but revealed that mysterious dark energy comprises 70% of the cosmos, while dark matter accounts for another 25%. The sobering reality is that our observable universe is 95% composed of components whose fundamental nature we completely ignore. Despite advanced technology and sophisticated experiments, the vast majority of physical reality remains utterly mysterious. This pervasive ignorance is not a failure, but the natural state of knowledge as it expands its frontiers. Gravity exemplifies this condition perfectly. It functions magnificently in practice, yet harbors mysteries that may be permanently inaccessible to human investigation. Learning to accept mystery doesn't mean abandoning the quest for understanding. Rather, it means recognizing that the search for comprehension is an endless process without a final destination. The journey toward knowledge is itself the goal, not arrival at some ultimate explanatory framework. Philosophically, this connects to Kant's distinction between phenomena, things as they appear to us, and noumena, the things in themselves that exist beyond human knowledge. Gravity might belong to this latter category, something we experience constantly, but whose ultimate essence lies beyond human cognitive capacity. Yet science has repeatedly transcended limits that once seemed absolute. String theory demonstrates that human minds can conceive mathematical structures of extraordinary abstraction, 10 dimensions, supersymmetry, exotic mathematical relationships. If we can conceive such structures mathematically, perhaps we can eventually comprehend them conceptually. The crucial question is whether mathematics captures the essence of physical phenomena or merely describes their observable appearances. Eugene Wigner wondered why the universe conforms so precisely to mathematical structures discovered by finite human minds. Some argue mathematical structures have independent reality. Others contend mathematics is human construction, making its effectiveness surprisingly mysterious. But even having complete mathematics doesn't provide satisfying understanding. Scientific explanation requires more than correct equations. It demands conceptual models, metaphors, and analogies that connect new phenomena to familiar experiences we can grasp intuitively. The curvature of spacetime is a useful geometric metaphor, but nobody can truly visualize four-dimensional curved geometry. Our brains evolved to navigate three-dimensional Euclidean space, so non-Euclidean four-dimensional geometries might remain permanently beyond intuitive comprehension. Some physicists argue the search for intuitive understanding is misguided. We should accept mathematics as our only reliable guide and abandon expectations that natural phenomena should make sense in everyday terms. Yet humans are fundamentally narrative creatures. We need stories, causal explanations that connect phenomena to familiar patterns we can grasp emotionally and imaginatively. This tension between mathematical rigor and intuitive comprehension pervades modern physics. Richard Feynman famously declared that nobody understands quantum mechanics, we just get used to it. This suggests deep comprehension might be impossible, and the best we can achieve is mathematical familiarity with fundamentally alien phenomena. Even accepting these limitations, we might wonder whether future intelligences will comprehend what currently escapes our understanding. Perhaps artificial superintelligences or cognitively enhanced humans will grasp mathematical relationships that remain mysterious to current human cognition. But regardless of future developments, for us now, gravity remains a powerful reminder that the universe owes us no explanations. The cosmos is under no obligation to conform to human expectations about comprehensibility. Mystery is not a temporary inconvenience to be eliminated through better theories, but an integral part of our relationship with reality. Perhaps this is as it should be. A universe completely transparent to human understanding might be smaller and less interesting than one that perpetually challenges our comprehension and forces us to confront the limits of what finite minds can grasp. Gravity teaches us that wonder and humility go hand in hand, that knowledge and mystery can coexist, that understanding means accepting that vast realms of reality will always remain beyond our reach. The force that keeps us anchored to Earth, that we feel with every breath and every step, continues to guard secrets that may be eternal. This doesn't diminish the beauty of scientific inquiry, but rather deepens it. We are conscious beings capable of recognizing our own ignorance and finding it fascinating rather than merely frustrating. The search continues not because we expect easy answers, but because questioning itself embodies something essential about what it means to be human. For us now, gravity remains a powerful reminder that the universe owes us no clear explanations, and that mystery is an integral part of existence itself. In the end, gravity becomes far more than just another physical phenomenon to be studied and cataloged. It serves as a mirror reflecting the deepest aspects of the human condition, revealing truths about our relationship with the cosmos that extend far beyond physics into the realm of philosophy meaning, and our place in an incomprehensibly vast universe. Here we are, literally held to the earth by a force we experience every moment of our lives, yet after 4 centuries of advanced physics, we cannot truly comprehend what gravity actually is. This inability to understand the most familiar phenomenon in our daily experience reveals something profound about the relationship between human consciousness and the cosmos we inhabit, but can never fully master conceptually. We are creatures who evolved to seek patterns, order, and comprehensible structures because our brains developed to find regularities that enhanced survival in specific terrestrial environments. Our ancestors needed to predict where water could be found, which plants were safe to eat, how predators behaved, and when seasons would change. Pattern recognition was literally a matter of life and death. But the universe did not evolve to be comprehensible to human minds. There's no a priori reason to expect that reality should conform to the particular cognitive categories that natural selection happened to install in primate brains over the past few million years of evolutionary history on one small planet orbiting an ordinary star. The remarkable success of physics so far might represent cosmic luck, a fortunate coincidence that the structures our minds can perceive happen to align with structures that actually exist in nature. But perhaps there are fundamental levels of reality that remain permanently inaccessible to minds shaped by the specific demands of terrestrial survival. Gravity may mark the frontier between the knowable and the unknowable, demonstrating that we can describe mathematically what we cannot comprehend conceptually. This distinction between description and comprehension is crucial for understanding what science actually accomplishes and what it cannot achieve. Science offers us extraordinarily precise maps of reality, but as Alfred Korzybski famously observed, the map is not the territory. Our gravitational equations are maps of remarkable accuracy and predictive power, but they do not capture the essential nature of the territory they describe. Description, however sophisticated, is not the same as ontological explanation. Medieval philosophers distinguished between 3 levels of knowledge: knowing that something happens, knowing how it happens, and knowing why it happens. Modern science has achieved spectacular success with the first 2 levels, but may be fundamentally limited when it comes to the third. We know that gravity operates, we know how to calculate its effects with extraordinary precision, but the deeper question of why mass curves space-time may lie beyond the reach of human understanding. Aristotle sought final causes, teleological purposes, that explained not just how things behave, but why they exist at all. Modern physics deliberately abandoned this quest, focusing instead on efficient causes and mechanical descriptions. Yet gravity challenges even this more modest approach because there is no known mechanism by which mass curves space-time, only mathematical description of this relationship, without any intuitive causal chain. This suggests that the search for underlying mechanisms might itself be misguided. Perhaps reality at its most fundamental level is irreducible, not decomposable, into simpler parts that can be understood separately. The reductionist dream of explaining complex phenomena in terms of simpler components may encounter absolute limits when we reach the bedrock of existence. Quantum holism, where entangled particles form indivisible systems that cannot be understood as collections of independent parts, points toward this kind of fundamental interconnectedness. The whole becomes irreducible to its components, suggesting that some aspects of reality can only be grasped as integrated totalities. Gravity might represent the supreme example of such holistic properties. Rather than being a localized force or mechanism, gravity might be fundamentally intertwined with the very structure of spacetime in ways that make it inseparable from the cosmic whole. Understanding gravity completely might require understanding the entire universe as a unified system, because gravity is not a separable part, but an integral aspect of cosmic totality. This holistic perspective resonates with philosophical traditions, particularly from the East, that emphasize the fundamental interconnectedness of all phenomena. Such traditions reject the Cartesian analytical approach that seeks to understand complex systems by breaking them into simpler components, instead viewing reality as an indivisible web of relationships. Paradoxically, gravity literally unites everything in the universe through the curvature of space-time. Perhaps our inability to comprehend it reflects the fact that we're trying to understand the very fabric that holds reality together. It's as if we're attempting to step outside existence itself to observe the foundations that make existence possible. This metaphor has limitations because gravity isn't a separate substance, but rather an intrinsic aspect of geometric reality. Yet it captures the intuition that gravity is too fundamental to be explained in terms of anything more basic, too woven into the structure of being to be separated from existence itself. Albert Camus wrote about the absurd condition of human existence, our search for meaning in a universe that remains fundamentally indifferent to human needs and desires. Gravity exemplifies a kind of scientific absurdity, our quest for comprehension, in a universe that may be inherently incomprehensible to minds like ours. But unlike existential absurdity, scientific incomprehension might be temporary. Perhaps the next Einstein will resolve what seems insoluble today through insights as radical as relativity was in its time. History teaches us intellectual humility. Every generation believes it stands near the threshold of complete understanding, only to have the next generation reveal new layers of complexity previously unimaginable. Aristotle seemed to have definitive answers about the natural world, but his physics was fundamentally mistaken. Newton appeared to provide the final word on motion and gravity, but his framework proved to be only an approximation. Einstein seems more nearly correct, but he openly acknowledged the incompleteness of his approach, particularly its incompatibility with quantum mechanics. Each generation of physicists believes it approaches final truth, only to discover that reality harbors deeper mysteries than previously suspected. This pattern might continue indefinitely, with each theoretical advance revealing new horizons of ignorance rather than approaching ultimate completion. Stephen Hawking once asked why the universe bothers to exist at all, a question that science cannot answer because it presupposes a perspective external to the universe that doesn't exist. Similarly, asking what gravity really is might presuppose a level of explanation that cannot exist logically, a first cause that has no prior cause, a foundation that rests on nothing more fundamental. Perhaps we must accept that certain questions are too deep to admit answers, that some characteristics of reality are simply given, brute facts that are irreducibly fundamental. This acceptance is not intellectual surrender, but rather a kind of maturity, recognizing that human finitude necessarily implies limits to what finite minds can comprehend. We can continue investigating gravity, searching for quantum theories of gravitation, probing the nature of singularities, without the naive expectation that complete understanding will ever be achievable. The value of scientific inquiry lies not only in the answers we might eventually obtain, but in the very process of questioning, learning, and expanding our horizons, even when the ultimate horizon remains forever beyond reach. In this light, gravity transcends its status as merely another physical phenomenon. It becomes a symbol of the human condition itself, representing our situation as conscious beings exploring a vast and mysterious cosmos with mental tools that are limited but admirably ingenious in their evolved adaptations. Our failure to comprehend gravity completely doesn't diminish the scientific enterprise, but rather ennobles it. It shows that the quest for knowledge continues, that mystery remains an essential feature of existence, that our capacity for wonder and admiration survives even our most sophisticated theoretical achievements. Gravity keeps us anchored not only to the Earth but to a fundamental truth about our place in the universe. We are explorers in a realm that transcends our understanding, seekers after knowledge in a cosmos that perpetually exceeds our grasp, conscious beings capable of recognizing our own limitations and finding them beautiful rather than merely frustrating. The force that pulls us toward the ground with every step also pulls us toward humility, toward recognition that the deepest truths about existence might always remain just beyond the reach of human comprehension. Yet this limitation doesn't stop us from reaching, doesn't diminish our wonder, doesn't reduce our appreciation for the magnificent complexity of the reality we're privileged to explore, however incompletely. Our failure to understand gravity completely doesn't diminish science, but ennobles it, showing that the quest for knowledge continues, that mystery remains, and that wonder about the cosmos survives. If you're still awake, it's because the content was really good. So take a moment, leave a like, and subscribe to the channel. It helps a lot. And if you want to keep watching, just click on the video that's appearing right now. I'll see you there.